Hi everyone. I'm sorry for the lectures. There was a delay in the lectures because I had to figure out some issues here. I'm sorry for that. I'll try to make it up within this week. We have 3 weeks of lockdown now, so I'll make more and more videos right now. And we will also have live classes. The only reason is I don't have very good Wi-Fi connection at home at the quarters, so which is the reason I'm not able to have a live class. The network is not very stable here, at least where I stay. Which is why I'll better post it through recorded videos as long as we can, and when the network and everything gets fixed, I'll switch over to we'll at least have a few direct classes live classes wherein at least we can have some tutorial problems kind of thing, wherein you can post questions and I can answer them. So right now for YouTube, I'll be posting these videos on YouTube. You're already watching that channel. You can post your questions as comments in the video section. Okay, I'll answer those questions. I'll make a video. In the next video, I'll be answering those questions. So far what we have, I'll just quickly list out what we have done. We have finished cellular concept. I have introduced you what is called as a cellular concept. Also, when we said, in the first few lectures, almost I think we spent 7 or 8 lectures discussing the basics of digital and analog communications. And then we started discussing wireless communication, some standards. I gave an introduction to wireless standards. And then we discussed a little bit about channel access and duplexing methods. So I have made videos till duplexing methods, meaning I haven't made videos for channel access. So I thought I'll start with the video of channel access now. And then I've also, in the lectures, as far as the classroom lectures go, I've also finished the cellular concept, so which is dividing the McDonald's idea of dividing a given area into cells, and then using the idea of frequency reuse and all that. How do you increase capacity with a finite number of channels? S is the number of channels. How do you support increasing number of users? A large number of users. How can you support that? I'm almost done with that topic, except two topics. A very small component called trunking and grade of service is remaining in it. So which I'll be very soon, probably in a day or two, I'll send the videos for it. So there are 2 topics which needs to be covered in this. So with that, we'll be finishing the cellular concept. And after that, once these 2 are done, I'm going to move on to wireless channel models. Probably this week itself, by this weekend, we'll be moving to wireless channel models. And once we go for wireless channel models, there we'll be spending some good amount of time understanding the probabilistic nature, statistical nature of a channel, and what is the difference between a wired channel and a wireless channel. Okay, and we'll spend some time studying. I'll do a very small example of bit error rate in a wired versus wireless channels. So I'll do a bit error rate analysis for a wired. We have already done bit error rate. What we have done so far, especially in the your first assignment, was also based on bit error rate, and that was for more of a wired communication or line of sight communication. When there is no line of sight paths, what happens to the signal then? So for that, you have to do a separate kind of analysis. So that's what we will be discussing that, and we will compare both the schemes. Then after that, we will go to modulation schemes used in popular wireless communications. So all the modulation schemes like DPSK, offset QPSK, pi/4 QPSK, there are different modulation schemes which are all very popular in wireless communications especially. So historically many were used, Gaussian FSK, Gaussian MSK. So these are different wireless modulation schemes, and we will spend the remaining lectures, so I'm going to divide it between wireless channel models and wireless modulation schemes. And then finally, I'm just going to, in this course, I'm not going to touch much about OFDM. I'll just introduce to OFDM and leave it. Very, very brief introduction to OFDM. That's what is the plan as of now, but we'll see how it goes. But my plan is the plan I had was that I had a lot more to be covered in this course. That was my plan initially. But once I'm executing the course, what I'm realizing is that there are 2 ways in which we can proceed with the course. One is we go deeper into the smaller number of topics, or we just touch upon very, very basics. Touch upon the basics of a large number of topics. I'm going to choose the first approach. We'll study limited content, but it will be done in depth. Next semester, there is a very high probability that I'll actually float an elective, wherein I'll start the course with OFDM, and then we will go to MIMO, and there are some transceiver problem. How to realize at a system level transceivers for wireless communications, and what are the advantages. I'll tell you what are the advances which has happened from 4G to 5G hardware, from a hardware point of view. And these 3 topics will be the major topic of discussion. in the next semester's course. So where I'll spend considerable amount of time on OFDM. Almost 25% of the course will be on OFDM. Okay, so right now we'll spend I'll just go back to, mainly I'll be focused on bit error rate in wireless channel. How do you model wireless channels, bit error rate in wireless channels, okay, and the modulation schemes. How do you analyze the spectral efficiency? I mean, we'll see how good they are, what are the bit error rates for wired versus wireless. So I thought it's good to actually have a good comparison for both wired and wireless communications in terms of bit error rate. Okay, if we have time, finally we'll see whatever remaining time we have after these two are finished, we will go to OFDM. Okay, I'll give a brief idea of what OFDM is, because any introductory wireless course just touches upon that. So I've seen the syllabus in most of the universities, they just touch OFDM and leave it in a wireless communications course, introductory wireless communications course. In an advanced course, yes, the next semester's course, if it in all likelihood it might float, but I'll try my best to offer it, but that will be the topic. We'll start with OFDM, discuss about MIMO, and this course will require a good understanding of linear algebra and probability theory. Okay, so that's for what I'll be discussing. Now, I'll come back to what I'll discuss in this lecture, which is about channel access methods. So I've already discussed it in lectures and I've made slides for this, but I thought I'll just discuss a few points. I don't know if I've discussed everything or not. I might have missed a few things in the lecture or in the slide, so I thought I'll just discuss it off. So before that, I made a video on duplexing, TDD or TDD and FDD, so which spoke about the duplexing method. What it says is that if I have two devices which are trying to communicate, or n number of devices which are communicating with each other, then TDD and FDD just tells you about the fundamental, at a system level, they tell you how can they transmit and receive. They don't tell you how exactly they transmit, how exactly they receive, but then they can tell you whether the transmission and reception can happen simultaneously or not. Okay, that's the only thing TDD methods will tell you. But it also tells you about some few hints it gives you about the system. It tells you whether you can have a device-to-device communications or not. So if you recall, I said most short-range wireless communications like Wi-Fi, Bluetooth, these systems end up using TDD because you need a device-to-device communications is possible in TDD. In case of an FDD system, there is a separate transmit band of frequencies and there is a separate receive band of frequencies. So we discussed that you can need to have a separate, I'll assume this is lower frequencies, frequencies increasing in this direction. This is transmit band and this is receive band. Okay, and we said that the Wi-Fi devices or any device have once it has an FDD system, Wi-Fi doesn't have FDD. So in that case, they'll need two separate bands for transmission and reception. Cellular systems. So for example, first generation, second generation, third generation, okay, 3.5G, all these generations had separate, and even fourth generation, they had separate transmit and receive bands. But in fifth generation, we are actually trying to move to TDD. It has some advantages. Of course, we know the obvious advantages of TDD. The transmit and receive filters will become much simpler. There is no duplexer filter. You just need a switch, and switch is definitely much less lossy compared to a switch at in an FDD system. Okay, and the only difference, how do we solve it? We don't transmit and receive simultaneously. So that's it about the duplexing methods which we discussed. So what it tells you, it just tells you whether the from time domain point of view, there is both ways of looking at it. If you look at it from time domain, it just tells you whether transmission and reception, I'm going to call TX as transmission and RX as receiver, whether they can happen simultaneously or not. Or from frequency domain, you can say that if they are separate, if there is two separate frequency band and receive band, then it is an FDD system. Okay, for a TDD system, it will be same. There will be overlap in frequency, but in time there will be some kind of orthogonality. Okay, in case of an FDD, there will be overlap in time because they can simultaneously transmit, but in frequency there is a orthogonality. So transmission and reception are two different operations, so you need to have some kind of orthogonality to distinguish them. Okay, so when I say distinguish them, distinguish the transmitted and the received signals. Otherwise, you will start, it's a wireless system, you can receive your own signal, right? So to distinguish them, then you need to have some kind of orthogonality. We also discussed that recently, the one that has gained good attention is full duplex. So recently, one of the a startup company has released a product with a full duplex transmit receive structure, which is one of the best in the market right now for 5G infrastructure. It's a very good one. It's a company called Maxcom. It has released a product with full duplex, and I also discussed what is full duplex. You can go to the previous video and watch it. Okay, when I say full duplex, your frequency bands are also same, and also you can transmit simultaneously and receive simultaneously as well. So it combines the best of both TDD and FDD. Okay, so that is something you can study about. Go watch the previous video, you'll understand it. So right now our goal is to understand what is channel access schemes. So meaning we just told whether the two devices can transmit and receive simultaneously or not. So that's the only thing that we discussed so far using the duplexing methods. Now how do they communicate? At a system level, if we want to answer the question, how do multiple users communicate in a wireless system? Okay, so that's the question that we need to answer. So how do you distinguish different users? So for example, let's say we didn't do wireless modulation. So if you recall from the previous introductory lectures on amplitude modulation and frequency modulation, we said the aim of wireless communication is that you have a low frequency data which with a bandwidth centered around origin centered around the DC or low frequencies. Now you want to transmit this wirelessly over a long distance. We said that the size of the antenna or the area of the antenna is proportional to the wavelength square. For efficient root radiation, it needs to be in the order of the square of the wavelength, or the dimension should be in the order of the wavelength of the signal. Okay, the electromagnetic wave. Now a low frequency signal will have a large wavelength, so which means the dimensions of the antenna becomes unreasonably large. So that is why we said we go for modulation. Modulation also helps in other advantage, namely that, for example, let's say I had n users with say M1, M2, each one of them transmitting n messages. Let's say I'll just assume that there were n transmitters and n receivers. Okay, so each person is supposed to just transmit like this, and everybody is transmitting wirelessly, which means if it is wireless, then this guy can receive all the n signals. I mean, he can receive, each receiver can receive all the n signals. Now how does he distinguish? He has to know that only this guy, he has to receive only this guy's information. How does he know that? So you need to introduce some kind of distinguishing factor, or since we are all now done little bit of communications, I'll use the word orthogonality. Orthogonality means that there is some kind of a distinction. They both are not, you cannot represent one as a function of the other. So they both are orthogonal to each other. Okay, so some kind of orthogonality has to be there. Okay, now one of the simplest methods, let's say I tell you that, okay, I don't mind building an antenna with a very large area. Okay, can you actually build it in a wireless system? Can you wirelessly transmit the low frequency data still? Even let's say we are able to transmit it, can you still transmit it? The obvious answer, of course, the area of the antenna is no longer an issue. Yes, you can. That is using a principle called time division multiplexing. So what we will do is that, okay, there are n users, n of them want to communicate. You will say there will be a central clock. A master system will tell you, okay, look, for the first, let's assume they're all communicating for 100 seconds. So I'll say 10 seconds I'm going to give for the first guy, 10 seconds for the second guy, 10 seconds for the third guy, and so on till the 10th guy gets, the 10 seconds in the 10th slot. Okay, so this way he can transmit the data. Even wirelessly without modulation also, he can do it. The only problem right now we said is that the antenna sizes become impossibly large. In fact, you can't transmit a DC signal wirelessly. So that's an obvious thing. Okay, for a DC, the signal has to be constant. It has to be constantly received, and so therefore you can't transmit it wirelessly as a DC. So maybe you can say, let's say we have this data here. Maybe I can ensure the DC is removed and transmitted. I can just remove the DC content and transmit it. Okay. So this is one mode of transmitting. So here channel access scheme, what does it tell you is that whether a user at a system level, you will say at a very abstract level, what is the method by which the users are going to communicate with each other. Okay, so essentially channel is something that's existing in a wireless system. It's something that's invisible. That's in a wired system, you just have wire connecting two devices. If you have two devices, there is a wire connecting the two devices. Okay, so that wire becomes the channel. In a wireless system, it's air, so it's there all the time, but now how can I access that channel? Do I have access to that channel? There are different ways. For example, now that we are signal processing engineers, at least we have taken a course on it, that you know that a signal can be seen both in frequency domain and time domain. Now, if the channel bandwidth is infinity, you should question me what part of the channel can I access, okay? And similarly, at what time can I access this channel? So here, frequency and time are like resources that each user can be given, okay? It's something that can be given to each user. I think if you find it a little complicated, we'll just talk about that. But first, let me just introduce you to at a very, very simple level. So I'll just come back to this problem, wherein we said at low frequencies, can we transmit this data? Yes, the answer is yes, by using what we call time division multiplexing. I'm going to multiplex. So there is a very, very standard way in any textbook you will find it explaining this concept of time division multiplexing. So there are many people, groups of people talking to each other in a room, and now you want pairs of people, two of them talking to each other. Now, if everyone talks, there is going to be noise and you will not be able to hear out the conversation. Now, the best way to do that, to ensure that you can only hear out your conversation, is to actually ensure that you can talk it in different time slots. Okay, so each one of you can communicate in different time slots. So that's one way of doing it. So that's called time division multiplexing. Okay, the other way is actually what we call code division multiplexing. So meaning you can actually encode your data. So each one of you can talk in a different language. Each one of you can actually talk in a different language to each other. So then that's like coding. You're transmitting the same information, maybe the same bandwidth, but because you're speaking in different languages, maybe you can distinguish it somehow. Okay. Now, how do you do that? We'll talk about that later. So I'm just introducing you to this idea that we can do that way. The third one is maybe different people can talk in different frequencies. You can change the pitch, the voice of your tone. So then the pitch of your tone, then maybe you can still hear out. If two people are able to hear only one particular frequency, okay, then they both can talk only using that high-pitched voices. The other guy maybe he's sensitive only to low frequencies, then they can use a low-pitched voice to talk to each other. Okay, so that's called as frequency division multiplexing, which we'll come to in a very brief moment. So now I just started with the problem and said that, okay, the main problem was when you're upconverting a data, one of the main reasons why we said we will upconvert the data is actually because we wanted to have realizable antenna sizes. Frequency modulation also comes with other benefit, which is what we call frequency division multiplexing. So what we can do is, instead of upconverting all the data, all the M message signals to a single frequency, I'm going to upconvert each message signal to a different frequency, FC2. So M1 will be here, M2, M3, and so on. Each signal can be upconverted to a different frequency. Okay. So by doing this, I can transmit. That's one of the other main advantages of wireless communications, is that I don't need N wires. In a wired system, you will need N physical wires to have this kind of things possible. Okay, you cannot transmit it simultaneously. In a single wire, you cannot transmit it, all the M message signals. Okay, here we are assuming we don't know. If you know the message signal is a priori, then you can cancel it out. But if you know the message signal, there is no purpose of communication at all in the first place. Okay, so since you don't know that, you can't distinguish them. So in a wireless system, to distinguish them, what they do is each user is given a frequency slot. Each user now transmits at a different frequency. So this is another advantage of upconversion, wireless upconversion. Okay, you just, because the medium is actually shared by all the users. The medium is just one medium and it is shared by all the users. So which means you can listen to anyone. So then how do you listen to only the intended user? You know the user, you will know, for example, if M1 to M1, the device, each one of them will be tuned to FC1 and FC1. The carrier frequency will be same for both. So then this guy can receive it. So if you recall your correlation receivers, I'm just going to multiply it with the carrier frequency and down modulate the data or deconvert the data. Okay, demodulate the data. Okay, so this phenomenon is what we call frequency division multiplexing. Each user gets a different frequency channel. So this is what we will be talking about in a little bit more detail. So now we are going to use a word called FDMA, which is called frequency division multiple access. Okay, how are multiple users going to access the channel? Okay, by using a technique called frequency division multiplexing. So FDMA essentially is a frequency division multiplexing technique used by different users. So we'll talk about a little bit more details about what kind of a system we can have in case of an FDMA, what are the different methods of channel access method, and little bit more details of what an FDMA system is. Okay. So shown here, as we already discussed, mainly the aim of this course is to discuss about wireless communication systems. We said that if two devices want to communicate with each other, we need to establish a standard. A standard tells you what is the range and frequencies in which you can transmit your data, what is the transmit power, duplexing scheme, and all that. A standard gives you an information about all that. Now a standard normally will give you a band of frequencies in which you can transmit. So this is what your entire band of frequency. Okay. So this is your total band of I'll just see if I've used a notation. Okay, let me just, I think this is, yeah, I've used the word FB. FB is the total band available for transmission. Now what we will do is we will now figure out, of course, the total band of transmission. This is FB will be much greater than the individual message signal bandwidth. So FCH here represents the individual message signal bandwidths. So that is that if you take the Fourier transform of the message signals M1, M2 till Mn, the Fourier transforms of all that, if you take it, the maximum frequency content will be smaller than FCH. Okay, in fact I should write because if you take Fourier transform of M1, it will actually contain both positive and negative frequencies. Your FCH will be greater than 2B, the total band of frequencies. FCH is designed to be greater than 2B. So what you do in a frequency division multiple access system, it's an access strategy. So the word access comes from channel access. A channel is seen as a resource. Okay, so in frequency domain, this is the frequency domain view of a channel. In a purely FDMA system, every user gets to use the channel for any time. There is no restriction on time. The channel is available to the user. He can access the channel at any time. Okay, but in frequency there is a restriction. Each user only gets to use a certain range of frequencies called as channel. Okay, band, of course all the users get to use this frequency only in this band FB. In this band they get to use this entire, the users get to use one of the channels in this band. Okay, and in this band we divide the band into smaller channels and each user gets to use only one channel. Okay, so that's what the problem of channel access is. So what we will do is, in a fixed system, usually we will allocate, for example, if there are n users, I'm going to allot user 1, user 2, user 3, user 4 and so on till user n. Each channel will be allotted to each user and only that channel can be used by them individually. Okay, I can do that. Okay, or I can dynamically allot the channel based on the request. When a user wants to make a phone call, for example, a base station, when he tries to make a phone call, the request goes to the base station, and base station normally allots him a frequency channel in a dynamic way. Whatever frequency channel is available, it will just pick and give it to him. So that's more of a dynamic channel allotment. So this is static. I can always fix the channels and say, okay, you can access only this channel and so on. Okay, so in FDMA system, you are going to take the band and divide it into channels, and each user gets to access a small part of the channel. Okay, he gets a small chunk of the channel. Now, if you recall, FDMA is frequency division multiple access. The channel is available to him. The next question is, if you recall, in wireless systems and especially in cellular systems, users can talk and also hear. You have to both transmit and receive. Now, channel access scheme tells you, okay, I'm going to use small channels for each user. Next thing is FDD. Whether it's FDD or TDD, that's another thing that we need to answer. So I'm going to say, first we'll talk about FDMA and FDD systems. Okay, so which is what your first generation cellular phones, even your GSM phones, GSM had a kind of TDMA, but it also had different frequency channels as well. So we can see it as kind of an FDMA and FDD system. We'll come to that in more detail about GSM's the channel access and duplexing scheme. Okay, so this is FDMA and FDD system. Okay, so FDMA channel access tells you that each user gets small bands, small channels within a band. Now FDD tells you that there is separate transmit and separate receive band. So now this is your FDMA FDD system. Okay, in an FDMA and FDD system, you can very clearly see that the channels, you will be dividing the frequency into smaller channels, bands into smaller channels, and there will be a separate transmit and receive band. Okay, so by looking at this, you will know, okay, it's an FDMA FDD system, because the frequencies are divided into channels and it's available for all time, and there's separate bands for transmit and receive. So this is an FDMA FDD system. Okay, and if you watched in the last lecture about duplexing schemes, we said that there will always be a fixed channel spacing between the transmit and the receive bands. Okay, it's called the duplex spacing, and we are ensuring the duplex spacing because we can relax the duplexer filter, because realizing a very sharp roll-off duplexer filter is a big challenge. So we said that we'll always ensure we'll have a fixed distance between the transmit band and the receive band. So meaning, if let's say a user makes a phone call, a user is trying to make a phone call, then a base station is going to allot him this channel and this channel. It will give him a pair of channels, one for transmitting and one for receiving. It's going to give him 2 channels. Okay, the next user makes a call, it will give him this channel and this channel, because now the frequency spacing is same between the two. Okay, next user makes the call, let's say this channel is already occupied by some other user, then if the next user makes a call, it will give him this 4th channel and this 4th channel here. So the spacing between the 2 channels is always constant. Okay, so that's it about FDMA in FDD systems. So a little bit more details we'll talk about in FDMA and FDD systems. Now let's assume that we have 2 devices which are trying to communicate with each other. Now in an FDD system, there is a separate transmit band and there is a separate receive band. Okay, similarly, if these 2 devices are in the same place, in the same plane, meaning they both are using the same channel access schemes, which is say FDMA and FDD, and they both are operating in the same standard. In that case, both these 2 transmitters or both these 2 receivers will have the same transmit and same receive bands. So if this is transmitting in, let's say, this is the frequency in which this guy is transmitting, or I've shown the transmitter here. So FT, it's transmitting in this range. But recall, this device and these device, both these devices are in the same wireless standard, so they both will have same receive band. Okay, now it cannot receive FT, it cannot receive a frequency in FT, I mean, because your receive band is here now, but your transmit band is here. This device has transmitted the data. Let's say you both are in the same, covered by the same cell tower, is transmitting to both of you. There are 2 users who are trying to make a phone call in a single cell tower. Now as they are trying to make a phone call, the cell tower is going to assign him a transmit channel. So let's say it's assigning him the user is assigned one transmit channel here, and he's also assigned some receive channel here. I mean, let's maintain the same duplex spacing, so it assigns him this receive channel. Now this guy will also get a transmit and receive channel. The problem is the transmit and receive channels are non-overlapping. So this device cannot directly transmit it to this device. Okay, because the bands of reception and transmission are very different. So this device, for example, here can only receive if the frequencies that it is receiving is in this band, but this guy is transmitting it in this band. So someone has to take this data and then convert it into one of the bands here, shift it, frequency translate it into one of the bands here, and then retransmit it from the tower back to here. So that will become a received data for this the other receiver here. Okay, so that job is done by normally the cell tower. Okay, so in an FDMA FDD system, you need to do this frequency translation. In a FDMA FDD system, 2 devices directly cannot interact with each other directly. Okay, in fact, not FDMA FDD system, in an FDD system itself, they cannot interact directly. The moment you go for an FDD system, the transmit and receive bands are different. So therefore, you need some device which can actually take the data, convert the data to a receive band, and then retransmit it back. Okay, you need some kind of a central device which can take care of that. Otherwise, you cannot use FDD. Okay, and here, okay, this is one other point which I've already mentioned in the class, but again, just to refresh it here. So mainly we are talking about cellular systems in this course. So you have a tower and a base station here, a mobile station here. Now both of them are trying to transmit and receive it to each other. Now we said that if 2 cell phones want to talk to each other, they will first transmit their data and to a cell tower, and cell tower will retransmit the data to this mobile phone again, to different mobile phone. Okay, so there are two transmitters here. So when, for example, when your cell phone is transmitting, this cell phone cannot directly transmit it to this cell phone. Okay, in a cellular system, the data has to go through a cell tower. So first the data is transmitted to a cell tower. The cell tower retransmits the data to another cell phone. Okay, so now there are two kinds of transmission that's happening here. So cell tower can also transmit, and your mobile station will also transmit. Now we are going to allot a transmit and a receive band for your cellular phone. Okay, so you should recall that the receive band of this mobile phone, which is same for both the mobile phones, will be the transmit band for the base station. So your base station or your cell station, the cell site, it's going to retransmit the data back to another cell phone, and that data has to be in the RX band, right? Only then this cell phone can receive. Okay, so in an FDD system, we know that they both are different. Now the question is, which band will I give for the cell phone to transmit, and which band can I give for the base station to transmit? Okay, so for example, if I say this is the TX band for the cell, this is for mobile station, this will be the TX band for the base station. Okay, so this will be the RX band for mobile station. Okay, and this is TX band for mobile station, and this will be RX band for base station. Base station will receive in this frequency. So if you recall the discussion on path losses, we said that the path loss increases with frequency of the signal. Now a mobile base station is a fixed base station, and it gets its constant power supply, okay, from some electrical grid network, okay, or maybe a very strong battery on a wireless. So sometimes you have base stations which are mobile, so and those base stations are normally powered by very powerful batteries. Okay, so the power is usually not a constraint for base stations, but for mobile handsets you have to charge it. Right now there is no widespread wireless charging, but it's going to come soon. But as of now we are relying on wired charging. So since we are relying on wired charging, you have to charge your cell phone again and again if you lose your power. So which means you will try to minimize the transmit power as much as you can. Okay, so mainly most of the power goes in transmitting the signal, because you have to transmit it for longer distances, which means you have to spend a lot of power. So, but you have to minimize the power as well, because you don't want to keep charging your battery again and again. So to do that, we will try to do every possible way of reducing the power. So one way we discussed, if you recall in the previous lecture on link budget analysis, we said that we will make the sensitivity of the base station very, very low. If you reduce the base station sensitivity, then for the same bit error rate, you can have a lower transmit power for your mobile station. So this is something we already discussed. Okay, so now the other point is that we said the losses are frequency dependent. Now if you recall, now coming back to this discussion, we said that whatever is transmit band for one guy, it can be mobile or base station, will be the receive band for the other guy. Okay, now I have to pick one of them as a transmit band, one transmit band for mobile and one transmit band for receive, the base station. Now we know that base station has a lot of power. It can afford to transmit at higher powers, and it can afford to increase. It can afford to be, it's fully always charged, so it doesn't have to worry about power. So therefore, I'm going to pick the band which is at a lower range for transmission for the mobile station. So in this case, I've shown here in blue, this is at a lower frequency. The frequency is increasing in this direction. So the one is at a lower frequency will be given for the mobile station. Okay, so there are two main things in FDMA and FDD systems. When you have FDMA and FDD systems, especially in FDD systems, you need to do the frequency translation for communication between two devices. So two devices cannot communicate with each other directly. So in an FDD system, that's a limitation of FDD system itself, not necessarily FDMA. It's a limitation of an FDD system itself. Okay, and the second thing we also discussed, the moment we talk about FDD with an FDMA, we talked about if you are going to give TX versus RX band, which device will get the lower bands. Obviously, we are going to give mobile stations the lower transmit bands, because the power losses will be slightly lower in that band. Okay, so and we are trying to minimize the power dissipation or trying to save the battery life of the mobile station as much as we can. Okay, now the other main problem in FDMA and FDD systems is the same problems that exist in FDD. normally we have what we call as a duplexer filter, because your frequency, the reception and transmission, we said that there has to be some kind of orthogonality, and that orthogonality is now in frequency domain. So which means they can receive and transmit simultaneously, but they are distinguished in frequency domain. There is a separate band for reception and transmission. So normally, to ensure that we don't send any transmitted signals into the received path, we introduce what we call as a duplexer filters. The duplexer filters are essentially band pass filters covering your receive and transmit bands. Okay, so these duplexer filters can be pretty bulky. They are pretty expensive, pretty bulky. The other major problem is losses. Okay, the typical losses will be of the order of 3 dB. 2 to 3 decibels will be the losses of duplexer filters. Okay, now the losses in duplexer filter means that, let's say it's a 3 dB loss. If you see, then imagine normally in a transmitters you will have a circuit called power amplifier, which will be eventually sending your signal to an antenna, and that will be transmitted. So if you're so before it goes to the antenna, there will be a duplexer filter. So you will encounter a filter and it will go to the antenna. Now previously, let's say I want to transmit 1 watt of power through an antenna. Your power amplifier output will be 1 watt, but as it goes through the duplexer filter, the output of the duplexer filter will only be 0.5 watts. It will be reduced by half. 3 dB means half in power. Okay, so now what will you do is that you will double your power amplifier power to 2 watts, so that the output of the duplexer filter is 1 watt, because you need 1 watt power in the air for you to work properly, for the system to work properly. Okay, so that's actually quite a big number. 3 dB means it's like almost doubling the power. So you'll be losing out your battery within half the time. So let's say because of this insertion, if let's say I didn't have a lossless filter, let's say I had a lossless, meaning there is no loss in the filter, in the duplexer filter, then I could have had a longer battery life. But now, because of 2 to 3 dB loss, which is 50% power loss, I'm going to have a shorter battery lifetime. Okay, so that's the problem here. So the duplexers also increase, something called noise. But right now I'll not talk about it. But if I'll just give a very simple intuition, if you don't understand, it's still fine. So when you're receiving the signal, the duplexer filter is like a attenuating system. So meaning it's going to reduce your power by half, by a factor of half. Okay. So voltage signals will reduce by a factor of 1 by root 2. You can see power will reduce by a half, so voltage will reduce by 1 by root 2. So now usually receivers add noise. Okay, the circuits that you build will have some noise that will be added by the receiver. If I am going to refer to, say this is your duplexer filter, this is the receive signal is moving in this direction. So the gain of this is half, gain square is half, because power gain is half. So let's say noise power Vn square is added here. If I want to reflect it at the input of the duplexer filter, then I'll have to multiply the noise by 2 Vn square. Okay, so that when I pass it at the output, I should have Vn square. Okay, so when I multiply it by half, I get Vn square at the output. So you can see that it's actually going to increase the noise level. It's going to amplify the noise of the receiver. It's going to, when it's receiving, it's attenuating in this direction. Okay, I can also see it's attenuating in this direction. I can also see it's going to amplify in this direction. See, receiver, you're not supposed to send in this direction, but I'm just giving it, this is an intuitive way of understanding it. If it's going to reduce this signal by 3 dB, it means that it's amplifying the noise in this direction by 3 dB. You can see it that way. So anyways, if you don't get that point, it's entirely fine. If you got it, it's good. Okay. So the main thing is duplexer filters introduce insertion loss. That's a problem with FDD system itself. Okay. That's why we said whenever we want a cheaper transmit receive systems, we normally go for TDD. Okay. And TDD also gives you a device-to-device communication capability. Okay, you can directly communicate between 2 devices. You don't need another device to frequency translate your data into a receive band. Okay, and we have already discussed in FDD system, the losses that these duplexers introduce is generally more than the losses that a switch will introduce in a TDD system. The next more important thing is user capacity. This is nothing but the number of users that you can support. See, this is not your channel capacity. Channel capacity is in bits per second. That's a different thing. This is in wireless systems, especially when you're going to cater to a number of users, you want to cater to as many users as possible. Okay. So this term user capacity is something we'll be using again in cellular systems a lot. So we'll talk about it at that time in more detail. Right now, here we discussed that we have a band and we are dividing it into channels. Okay. So if FB is the total width of the band, so this is the total available band is FB. Okay, and I'm going to divide it into small chunks, frequency chunks of width FCH. Then the number of users you can support is FB by FCH. M is the number of users you can support. Simultaneously, you can support so many users. Okay, so I've taken one example of GSM, and I said that the band of GSM is 25 megahertz wide. So this is 25 megahertz for GSM. We'll probably, when I discuss wireless standards, we'll actually see what does this band mean. Okay, for 25 megahertz. There will be separate transmit and receive bands, but I'm only showing one now. Okay, see, if you find the number of channels in the transmit band, that's going to be same. Most of them are symmetric allotment. We are allotting symmetric channels in both transmit and receive bands. So if you find the number of users in transmit band, it will be same in receive band as well. Because recall, whenever your user is going to ask for accessing the channel, you are going to give him a pair of channels. I'm going to give him a receive channel as well here. So there is a receive band here, and I'm going to give him a pair of channels. Okay, so the resource that the user gets is a pair of channels for all time. In a purely FDMA system, he is going to get the resources for all time. So if you take an example of a GSM system with 200 megahertz as the total bandwidth and 200 kilohertz as a channel bandwidth, then the number of users you can support is 125. Okay, so but a practical GSM system will support much more than that. We'll see later how does it do that. Okay, so in the purely FDMA system, the number of users depends on two things: your channel width. If you have smaller channel width, then you can afford to have more and more users. Okay, or you can increase your FB, the width of the channel itself, the band, available band itself. Even that way you can have more users. Now the problem is with FDMA is that we discussed that we need to have duplexer filters. There are two kinds of filters here. I've probably discussed in the last class as well. There is something called band select filter, which will be for each standard. For example, Bluetooth will have a certain band of frequencies. First generation, second generation communications will have certain band of frequencies. This entire band is called is the band allocated for a wireless standard. Now within the band, you will divide this into small channels. Okay, each user gets to access only this small channel. Okay, at least in FDMA he gets to use only this small channel. So usually your transmit and receivers will have two kinds of filters. One is called channel select filter and band select filter. So we'll talk about it when we talk about TDMA in more detail. Right now I'll just introduce you. So first, you can have multiple standards here. So for example, another standard can have a transmit band in this region and in this region. So your devices, two wireless devices which are compatible with a given standard, should only take the desired band of interest into the system. So you will first have a filter as soon as the antenna is entered, the signal enters the antenna, you will first have what we call BSF or band select filter. That will select this entire band of frequencies. Then ideally you will need what we call channel select filter. So this is at RF frequency itself, we can have it. So you can directly have at a much narrower frequency. The bandwidth of the channel select filter will be much narrower. That width has to be approximately the channel frequency width. The width of the band select is much larger than the channel. It can be relaxed, but channel select filter will be very, very narrow. Okay, so generally when you see FDMA, it is used in systems with very large bandwidth. Example where FDMA is popularly used is Wi-Fi. Wi-Fi is a place where we see a popular usage of FDMA. Okay, a modified version of FDMA is used, but I'm just giving an example where it is used. For small bandwidths, if your channel bandwidth is very, very small, then the channel select filter has to be really, really small. Okay, so for that it's very difficult to realize low bandwidth, meaning your filter needs to have a very good roll off. It should have a very low cutoff frequency. Okay, and that's very challenging to realize. Low bandwidth, high roll off filters with low bandwidth and also very tight roll off for those low bandwidths. Okay, so that's very tough to realize. When I say roll off, what do I mean is that it's the attenuation, how fast the signal is actually rolling off from once let's say you encounter a pole, your filter response will start reducing. So the rate at which it falls off, roll off gives you an idea for that. A good filter needs to have very high roll offs. Okay, a good band reject filter or a filter that can reject some frequencies, it should have very good roll off. Okay, so if the roll off is poor, then it's going to look like this. So you are passing all these frequencies which you still don't want to. Okay, Now, in a low bandwidth system, FDMA is not very practical because of bandwidth reasons. So we discussed one main thing, which is FDMA in FDD systems. It's very important. I discussed only in FDMA and FDD systems because there is a concept of frequency translation, which is performed by a central intelligent device. For a cellular communication, it happens to be the tower. Tower does that operation. You can also have FDMA in TDD, a time division duplexing system with FDMA. Now, how do you recognize that? You can let me just explain it here. So, in an FDMA TDD system, you will just be given one band. Both transmit and receive will have just one band, but each user will get a channel, a smaller channel. So, in an FDMA TDD system, I can actually have an FDMA TDD or FDMA FDD system. Okay, Wi-Fi can be seen as a kind of an FDMA TDD system because it only has one band. There is no separate transmit and receive bands. It's just one band which it has to access. Okay, so because you don't transmit and receive simultaneously, which is what TDD is telling us, you can just have one band. You can transmit and receive in the same band of frequencies. Okay, and the only advantage of going, again, of course, when I go for FDMA and TDD systems, the advantages I get, obviously, that TDD systems brings in, which is there is no duplexer filter, it's only a switch. Okay, and also I save on bandwidth, almost twice the savings in bandwidth. Usually I'll need a separate band here. Every time a user makes a call in an FDD system, I have to allot him a pair of channels, channel here and channel here. But now I don't have to do that in a TDD system. I can only, the loss is that they can't transmit and receive simultaneously. Okay, so whereas the example of FDMA TDD is Wi-Fi. Wi-Fi is a classic example of FDMA with TDD. Okay, as I said, it's not a straightforward FDMA. It has some more complicated FDMA. It's there is a different multiple access called packet radio, which is but it's still at top level. You can still say it uses some kind of an FDMA access, multi-channel access scheme. So we'll go back to, now we have discussed about FDMA, okay, so which is one form of accessing the channel. Okay, we also found how many users you can support. If you know the channel bandwidth and the total band of frequencies, then you can find the number of users you can support. Then we discussed about FDMA FDD, which is a little bit more complicated to implement. And we said we need a central device to up convert and down convert, translate the transmit to the receive band and all that. Okay, and we said two devices cannot communicate directly with each other in an FDD system. We also discussed very briefly about FDMA with TDD. Okay, FDMA with TDD, you just have one band. For example, I can show this. This can be used both as a transmit and receive bands. So you are saving on bandwidth. Okay, and you get all the benefits that you get with the TDD system. No duplexer filter, just a switch. Okay, and device-to-device communication is possible. Examples of FDMA TDD, I said a crude example is Wi-Fi. And FDMA FDD, we no longer use it. FDMA FDD is not used anymore. But the first generation of cell phones, the first generation of cellular phones, they used to use FDMA FDD communications. Okay, the analog communications, the first generation of systems, which in America it was called AMPS, if you recall. Okay, so that was the first generation of analog communication systems, which use a cellular concept and all that. So that used to use FDMA and FDD. So that's it about FDMA scheme. The next lecture I'll talk about TDMA.